So welcome everyone. Thanks for being here, here at Links and connected via Zoom. So many of you may know me, Lorenzo Maggi from Nokia the Labs. I used to come here more often before COVID. Afterwards it really stopped. But so I'm gonna talk about really some basics of wireless communication channel, especially. So indeed, I was telling Francois that so when I learned a bit better than let's say than what I used to know about this wireless communication theory a few months ago, I thought that there may be a few people that are in the same situations like me, that basically talk and try to work with the people that are expert in the domain, but there is clearly some barrier of entry and also barrier of jargon that one has to face at some point and overcome. So this is, of course, this is not. This is maybe too ambitious, but in, let's say, 45 minutes, I'd like to at least go through this basic terminology and what this means from quote basic principles. So first of all, why do we have complex signals? And what is a channel? What is channel response? What is a fading? You may have heard of slow fading, fast fading, flat fading. What is fading itself? Coherence time, Doppler spread, delay spread, coherence band with intersymbol interference baseband. So I'm sure that many of you already know this or do not know, but for sure have already heard about it. So let's try to understand together really from really basics. And if you already know, please go back to your desk because it's going to be very boring. So you're welcome to leave. Okay. So yeah, how to move out this? Can I? No?
Si tu cliques sur tes transparences, ça marche pas?
No. Anyway, well, let's do this. So first of all, we have a wave that propagates in the space. You may think of it as a rope here, someone that is going up and down on an end. The rope itself does not move, but the wave on the rope does. So, so how fast does the wave propagate? So we have the speed, which is constant in the electromagnetic field, which is the speed of light. The speed is the distance over the time. The distance, we can define it as the distance between two peaks. Okay, and how long does it take for two peaks to appear one after the other? Actually, the time that it takes for me to go from a peak to another, which is called t. And 1/t is the frequency at which basically I go up and down with my rope. So basically the speed is c is lambda times f. So wavelength times frequency. And this basically pops up all the time, and it's really something that we have to keep in mind. C equals lambda f. I don't know why it doesn't. Okay. Please.
I'm sorry, but didn't you just say before that C was constant and it was the speed of light, and now it's not a constant anymore?
Yes. So the speed. So in electromagnetic field, the speed is always the same.
Okay.
But in general, can be can be different. I mean, if it's me that is actually going up and down with the rope, it's going to be smaller than C for sure. But yeah, in general, C is always is constant. So C for us is really the speed of light. then less.
The speed of light depends on the medium. So
Yes.
in the air, it's quasi equivalent to the speed of light, but for example, in fiber, it's 2/3 of c because of the medium.
Okay.
Medium make the speed of light shorter.
Okay. But in any case, here we're talking about over the air. So you will see I'll make a lot of approximations in any case. So just keep it. We can keep it simple. Let's start with the simplest case as possible. So fixed transmit antenna, and for us, the transmit antennas will always be fixed. It's base station, we say. And fixed mobile, so fixed receiver, and the antenna transmits to the receiver. So indeed, the antenna transmits an electrical field that oscillates according to, let's say, a cosine law. This alpha, actually, we could go on for hours talking about what this alpha is. For us, it will just be a number, a real number. But for you to know, because for sure that you have heard many things about wireless already. So basically, alpha is the antenna gain in elevation and azimuth. I hope that my visual explanation is enough. But yeah, let's not worry too much about alpha. And what does the mobile receive? Basically, a replica of what the base station is sending, but with a small difference, which is this RC. So R over C is actually the propagation delay. Basically, the mobile sees the same thing that the base station was transmitting R over C second before ago. Okay, so it's just the translation of. Okay, so for now, nothing really extraordinary. So the amplitude of what the mobile receives is always the same. It's just that you have to take into account for the fact that you're not exactly at the base station, that it takes some time for the wave to propagate. Yes.
Actually, just a quick question.
Yes.
So there's this 1/r factor
Right.
in the
I forgot.
receiver.
I forgot.
I would have expected the 1/r2, for example.
Yeah, R2 for the.
This serves the explanation.
The power is the square.
Exactly.
Okay.
The power is a square.
Okay.
So here it's really the electrical field itself. So it's volts. And by the way, we'll not delve into it, but it's not always R squared. The power can be much more. So R square is really the most
Without any obstacle.
the largest case. Exactly. Without any reflection.
Yeah. It's to avoid as long as you have air.
Exactly. Yeah. Just because basically you have to. So the energy stays the same, but the volume. So actually, yeah, the area grows as R2. So basically, the power decreases by the. Sorry.
The fading exponent will cover that later.
Yes. The fading is among what will deal.
Yeah, and this is also for the omnidirectional case, right?
Exactly. So yeah, here I'm starting really basic, and I'll stay very basic. So I hope it's not too boring for you, but at least it was not boring for me while doing this class, even though it was late at night. So anyway, then one step further, free space again, and moving RX antenna. So moving mobile. So what do we receive as a mobile? Basically the same thing as before, but accounting for the fact that the distance varies over time. Basically, we can think of the mobile moving along a line, and this distance growing linearly with time. Distances r0 at time equal to 0 and r0 plus vt as time t. So basically, the propagation delay is still distance over speed. And then you indeed find this term. So basically, it's the same replica, but translated over time. So and indeed here you see that basically the propagation delay changes over time. So basically, I'm not always seeing what the base station was transmitting 1 second ago, but 1.1, 1.2, 1.3. And what it means also that basically the frequency itself changes. Okay, because basically imagine that you're moving at the speed of light, then you will see always the same thing. So basically you will see you will no longer see a sinusoid. You will see a constant. Okay. Then okay. I will not talk about the relativity. It's really a toy example, but I see Ludovic that is joking. But anyway, so basically, what happens is that indeed we see a cosine with a different frequency, which is smaller. Smaller by a factor 1 minus b over c. Okay, so still nothing bad happens per se, in the sense that the amplitude is always the same. It's just that we are seeing a cosine with a smaller frequency. That's it. But things get worse in the following. Okay. So one step closer. Fixed RX antenna, a reflecting wall, but mobile that stays fixed at the certain point. So still the same, the base station transmits a cosine. What does the mobile receive? Actually, two replicas. The first one that is over the shortest path of length r. So basically, it will receive a replica delayed by r over c. And then another path that is delayed by basically d plus d minus r. So basically 2d minus r. Okay. Basically, the mobile will see two things that look alike, but they're not exactly the same thing, because indeed there are two replicas of two cosines with different shifts. And basically, the phase difference between these two paths is basically the difference between this thing and this thing. And okay, the algebra is really simple, but intuitively, what we have here, so the mobile will see a shift that is 2 pi times how many times the distance stays in the, so how many times the wavelength stays in the distance. So if the distance is exactly equal to wavelength, then the phase shift is exactly 2 pi, and then in proportional way. So basically, this is 2 pi r over lambda. So, and the other one is same thing, 2 pi over times how many times lambda stays in the path length. So you see that if I move by lambda equal to lambda over 4, the first path moves by lambda over 4. The second, but in one direction. The other one moves by lambda 4 in the other direction. So the difference is lambda over 2. Lambda over 2 is basically so it's basically the space that the distance that it takes to go from high peak to low peak. So basically this is why we call it coherence distance, because it's really the distance that you have to go through to see a significant change in the amplitude of the signal. So basically, if we take all this together, okay, yeah, I also wanted to say something more. So let's also talk about this delay spread. That is something that you may have heard many times. In this simple example, is just the time difference between the two propagation delays. And in general, the delay spread is the time difference between the maximum time difference between any two propagation delay that there may be. So you may think of many reflectors, and the time spread is indeed the time of the longest minus the time of the shortest. And coherence bandwidth, we will get back to it later, but it's basically the inverse of this delay spread. We'll understand better why this is the case, but basically you can think of it, delay spread and coherence bandwidth as the same thing. Delay spread is the propagation difference. Coherence bandwidth is the frequency, the frequency bandwidth over which the yeah, maybe this is I mean, I'm assuming too many things now. So let's talk about the coherence bandwidth afterwards. So if you go back to the example before, and we basically get everything together. So we have a reflecting wall, we have a mobile that is moving now. Okay. So we have two paths. So the mobile is moving towards the wall, and we're also assuming that it's fairly close to the wall rather than close to the base station, such that R0 plus Vt is roughly equal to D, such that the denominators look alike. So basically, you can approximate them as the same. So basically, in this case, you can sum the numerators. Basically, what you're summing is two cosines of slightly different frequencies. Because basically, when you're playing guitar and your friend or yourself has basically a chord that's slightly off tune, you play the same chord, and you hear wow, 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 right? So it's basically the same thing. So the superposition of two cosines of slightly different frequency is basically the multiplication of two sines. One that is wonderful animation. So one that is slow, and the other one that is fast. The fast one is exactly the same frequency as the initial signal, and the slow is at the frequency that is indeed the difference between the two frequencies of the first path and the second path.
The first one is the average.
Is the average, yes. But yeah. We're exactly. This is the average. But I mean, you can think of it as so the Doppler spread usually is in the order of 50 hertz, and the frequency is maybe gigahertz. So, but yes, this is the average. And indeed, yeah, I mean, you can prove this very easily by basic trigonometric properties. So you write the cosine as is j plus e minus j over 2. And indeed, you take the average out, and basically you have this plus that times this. So indeed, so this is already we can call it already fading. So this is actually what is called fading. It's not exact. So we will get back later. It's not exactly what let's say the wireless community mean as fading, because we have to take one step closer or two steps closer to reality. But by this simple fact, you can already understand more or less what fading is. It's basically the fact that the intensity of the signal changes over time due to the fact that you're moving and there are multiple paths that superpose. And there are some paths with different frequencies that increases with respect to the carrier, some paths over which it decreases, and this fact generates the fact that there is fading. Then, so now, so we'll move away from this, let's say, toy example, and we're trying to be a little bit more formal, even though, I mean, there's no, actually, there's no proof at all, but let's try to make it a little bit more formal. So, first of all, we'll try to move out from this cosine, because indeed, transmitting cosine is nice for examples, but it's not what you really want to do. Is you have to transmit cosine times something that that is somehow correlated with what you want to say, what you want to transmit. So you will say that you will transmit x of t. In our case, x of t. The previous case is just cosine, and you receive y of t. Okay. Then, if you just take the toy examples of before, you see that they can all be written in this form. So basically, is a superposition of multiple replicas that are shifted over time and multiplied by some path laws, okay, by this AI of t. Remember, we were still everything is real. All numbers are real. And also it's continuous. T is continuous variable. So for example, for reflecting wall and moving antenna, we have this alpha 1, alpha 2, sorry, A1, A2, and tau 1, tau 2. And by the way, just notice that the derivative of tau over with respect to time times frequency is T over C times F, which is the Doppler spread that we said before. So just keep this in mind, because it will be nice to understand later on. So basically, you may have heard of channel response. What is channel response? Basically, is the convolution between the input. So the channel response is what is convolved to the input such that you have this output. So we have seen this y. If you convolve x with this guy, by the way, this is not equal, this is times, then you have this channel response, but that is basically or impulse response. And indeed, why is it called impulse response? You can think of it as the response of the channel when you just send an impulse, Dirac delta. When you send Dirac delta, what you have is you will have one replica A1 after tau 1, and the other replica A2 after tau 2. In our reflecting wall example, for example. And then, yeah, the channel response in frequency is nothing more than the Fourier transform of H. That in this case is just AI times the X of minus J F tau I. So if you know Fourier transform is really standard. You may have heard again about baseband model. So actually, this is really important because all the models in wireless are about baseband. No one really writes equations with the FC, the frequency carrier in it. So it's really important to kind of understand what it means, because indeed also it lends to nice and simple models. So the baseband equivalent model. So up to now, we said that we're basically sending something over the air at some frequency. Let's call it FC, which may be hundreds of megahertz or even gigahertz in 5G. We said that it's not exactly just a cosine because otherwise it would be boring. Already it's boring by looking at all this space, but we'll cut this part. So it's not really a cosine, but it's cosine times something, but something that has a limited bandwidth. Okay, so we can think of the signal that is sent or in the frequency as having a Fourier transform of this form. Why of this form? Actually, this is not the Fourier transform. Fourier transform is real and imaginary, so it's, you can think of it as just a linear part. But why of this form? Because basically, since it's real, we have to have this property of x minus f equal to the conjugate of x of f. So basically, you will have something symmetric in real, and in imaginary symmetric and flipped. So basically, you see that there is information that is replicated for high frequencies, for positive frequencies, and negative frequencies. The baseband model just say, well, why do we replicate the information? We just need, for example, the right part. The baseband model is basically the right part in frequency domain translated to and centered around 0. But this is no longer a real signal, because indeed, the real signal has to basically has to fulfill this relationship. So it's no longer symmetric over 0. So this is why we have imaginary signals. So this is why you see X complex signal in the papers, because indeed what we do in reality is to send at high frequencies. And at high frequencies, you have this possibility of sending cosine and sines, and cosine and sines are orthogonal. So basically, you can send different things on the cosine from the sine. If you go back to baseband, basically you no longer have this cosine and sine. So you have to deal it basically in other ways. You have to deal with two parallel streams at the same time. And let's say the most intuitive way is to assign something to the what is called the quadrature signal, with the one that multiplies the cosine as a real part, and the quadrature is imaginary, and the in phase is what multiplies cosine thing. Sorry, I'm mixing up. But by the way, you got it. So on the real, you take the one that multiplies the cos, and on the imaginary part, you take the signal that multiplies the signal. And basically, this is why you have complex signals. And so another thing that how does the baseband and the let's say over the air signal relate to each other? Basically, it's fairly simple to show it. So you write this guy as this XB the baseband translated at FC, plus the same thing translated at minus C, flipped and conjugated. Then you take the inverse transform, you have this thing. Basically, you realize that there's nothing more than the real part of the first term, because it's the first term plus the conjugate twice. So this is why you have.
I don't understand why do we have the square root of 2 factor here?
Yeah, it's rather it's a normalization, because basically you're saying that so yeah, it's just a normalization. Because yeah, the power of baseband should be equal to the power of
something. Yes, for power.
Exactly. You want to have that
Same power.
the same power between baseband and over the air. Exactly. Yes.
Can you explain again why you can send both the sine and the cosine at the same time? And I didn't.
Yeah. Indeed, this you can really understand it by this formula, this real part of this thing. So, and actually, I think that I have the response here. Yeah. So the real part of this guy is the real part of the baseband times cos minus imaginary part times sin. Basically, what you're really sending is cosine and sine times two different things, because indeed cosine and sine are orthogonal, so you can superpose them without any information loss. But this you can do at the frequency carrier. Then, if you want to indeed translate everything at frequency 0, you have to basically erase this cos and sin, and this is why you get back to some imaginary part. So what is done is in the practice you have a signal in baseband. This is what you really want to send, which is real and imaginary. You multiply it by cosine. This is an oscillator. You multiply by a cosine at frequency some gigahertz. You multiply the imaginary part by the same thing, d-phase by minus pi over 2. So basically it's a sin, minus sin. And then you send the sum. Then at the receiver, what you actually do is you basically do the same thing plus this low pass filter, because basically when you have to remultiply by cos and sin, but when you do that, you will actually find yourself with some replicas over frequency at a high frequency. So basically, in order to get back the original signal, you have to get rid of this replica. So this is why there's low pass filter. But basically, it's the reverse of what you do at the transmit. But this is really, I mean, I think that this, when you have understood this, you're already halfway through to any at least introduction of what wireless speak. Then I don't know how much time left. Okay. We still have let's say 10 minutes or 15. So baseband equivalent model. So let's take another step further. So remember that we have this equation that is at the frequency of gigahertz. Now we want to rewrite it at the frequency basically 0, around 0. Okay, and this is where actually all the signal processing is made. Signal processing is not made at very high frequencies. The signal processing is made at baseband. So this is why it's important to understand what really the baseband model is. So basically, from the first bullet point to the third bullet point, it's actually not so easy. Actually, to solve it, I have to actually find the solution somewhere and then understand it. It's they look like basically the same thing, and one can think, well, it's trivial. It's not. So it's trivial to show that the real part of this is basically the two real parts match, but to show that the two imaginary parts match, to me at least, it's not trivial at all. But basically, what we can prove, let's settle for the end of the story. We can prove is that basically the same relationship holds for frequency carrier and baseband, which is great, but with a twist. So this AI is no longer the path loss that we could very well understand before. It was just a real number. Now AI also takes into account for the dephasing. So AI is actually a complex number. Now we're really moving from the real world to the complex world. And basically AI is still a path loss as before, times actually the e to the power of this phase shift to the distance. So AI is really, it's not artificial intelligence, okay? It's basically path loss, the magnitude is path loss, and the phase is actually the phase shift due to the distance. So it really says everything about what you want to know about the path. And this and how do YB, so basically what you received in baseband and Y is what actually you received in over the air relate. It's basically the same relation as before that we've seen before over X. So basically Y of T is the real part of YB baseband times basically this thing that has frequency. So basically, we're dealing with something which is really fairly nice. So we are modulating things. We're multiplying by a cosine sine, and we're getting back to frequency 0, low pass filter, and basically we can think of it the end-to-end the end-to-end story basically looks like the story that I told you at the beginning with a two paths superposing with each other. So this is very nice, and you have an equivalent impulse response. Before it was just AI times delta of P. Now you have AI B. So basically the same thing, but in baseband. So basically now AIB is path loss and as magnitude and phase shift in the phase. Now the last step to quote unquote reality, even though I think that we're still fairly far from reality, but so you're not really, so when you talk about analog versus digital, you want to send digital information, not analog. So X of T, when you actually use an oscillator, is analog, but your information really is digital. So you have bits. You have bits that are coded into complex numbers, and you want to input these complex numbers in all this mess. So how to do that? So X of T is what you want to transmit in the continuous time. Since usually X of T has always a limited bandwidth that we call W, by classic Shannon-Nyquist theorem, basically you can sample X of T at the frequency W. So first of all, X of T has bandwidth W. So, but the X of T is what you send over the air. Then the baseband has a bandwidth that is W over 2, okay? Because basically you shift everything around 0. Okay. So you can sample at twice this frequency, which is W again. And basically you can sample it, and but then once you have sampled it, you have multiplied by sync, which sync is indeed a perfectly low pass filter, basically. And this is why indeed you can retrieve the signal that you had before by doing this. So so basically you have this thing. You can rewrite XB like this. Remember that we had this nice expression over YB of T. If we substitute X of B with our, let's say, digital counterpart, actually our digital counterpart is just XB of N, then this is still continuous per se, but we're really interested in X of B. if we plug this x of b in this formula here, and we sample indeed at every 1 over w, then we get this messy expression. But that can get fairly nice once again. You can rewrite this messy expression with two summations, sync of m minus n, blah, 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 as a convolution between, again, your symbols and what is called, again, channel response. We have seen already 3 channel responses. We have seen the channel response over there, channel response baseband but continuous. This is channel response sample, but which is really something very similar as before. But this is really the whole story. So if I think that the talk may even terminate here, saying, well, we have seen more or less how to go from cosine transmitted over here to something that looks like what you find in the page 1 of any wireless paper, where indeed your x of brackets m minus l, let's say m, is your symbol, complex signal that you want to send at time m minus l, and where this hm of l is your channel response. So if you forget about the m in the h, basically you have the channel. So it's basically the channel response at time L. So it takes into account the fact that indeed you have intersymbol interference. But the fact that there is M here basically tells you that this H of L varies over time. And this is where fading comes into play. Fading tells you that we saw before with the 2 frequencies that were different, slightly different from each other. Fading plays a role in making this HL depend on M, depend on time. And how you will see it later. Yeah, this breaks a bit the flow, but yeah, here I just wanted to say that if H does not depend on N, and H is always the same, so it's not time invariant, then you have a much simpler formula here. Basically, H of L, so your channel response, is nothing more than basically your HB, what we've seen before, and I don't remember where. Yeah, I shouldn't have put this here. Yeah, it's here. So this H of B convolved by a sink. So basically, you have to think of it as this HB with a sink superposed on each P, basically. Anyway, it's too much info in this line. So let's forget about this last bullet. But really the last, I think, very important thing that I wanted to tell you, I mean, everything is relative, but it is very important for this talk, is how to plug this fading concept into this formula. Let's look at really what this HM of L is. Really, every term is the summation of this mess. And the real question is, how does this mess vary over time? So you have 3 members. So three elements: AI, E to the power, and sync. We've seen that AI is basically the path loss, and path loss changes over time as 1 over R. And 1 over R, let's say, changes fairly slowly in the time scale of seconds. Let's look at this sync. Sync, what changes over time is this tau I. Tau I is the propagation delay. If I move from the base station, the propagation delay changes over time. But this tau I is multiplied by W, which is the bandwidth. And here you have this tau I, which is multiplied by the frequency. Usually bandwidth is some megahertz, frequencies is maybe gigahertz. So basically, this is much smaller than this. Okay, this is really hand waving, okay, but this is much smaller than this. So this is second, this is much smaller than this. So let's really look at the A to the power of. This is really the main actor that makes HM change over time fast. And how fast? So the speed at which it changes is inversely proportional to the coherence time. And actually, we've already seen coherence time before. It's the inverse of the Doppler spread. So Doppler spread is the difference of frequency of all my replicas. If the base station is there and I'm moving in this direction, I will see a wave with a slightly lower frequency and another wave with a slightly higher frequencies that is reflecting on the wall. So basically, you will have some e to the power of something that changes over time. And how does it change over time? With the derivative of tau with respect to t. And we've already seen a few slides back that derivative of tau with respect to t times f is exactly Doppler spread. Doppler shift. And the Doppler spread is the difference, maximum difference of Doppler shifts across all paths. So all this is hand waving, but I hope that you understood more or less intuition of why does it changes over time. And then the two last, let's say, terminology. Here we saw fade-in, sorry. Here we saw fade-in and coherence time, and we saw that the coherence time is basically the inverse of Doppler spread. Here, what I'm telling you about is about the delay spread. Delay spread is in time. Doppler spread is in frequency. Delay spread is time. Delay spread is the difference propagation time between the longest and shortest path. And the inverse of the delay spread has a very nice interpretation in the frequency. To see frequency and time always the dual of each other. Before you had Doppler spread in frequency, and the inverse of Doppler spread is something that has its occurrence time in time. Here, the delay spread is in time, and the inverse of the delay spread tells you how fast the channel response in frequency changes. So you see there is really this duality. Delay spread in time, inverse of delay spread is how fast this thing changes. And to really understand it, at least I understand it with a very simple example. Let's assume that there are just two paths with same loss, path loss equal to 1, say. So the no loss. The first path arrives immediately to you. Basically, you're really at the base station. The second one is 1 over 2w. Why 1 over 2w? You will understand it at the end because it's convenient. So h of f is basically the summation of 1 times e to the minus 0, so 1, plus 1 times e to the power of this guy. So absolute square basically is this guy times this guy conjugate. You have a 2 you have another, so sorry, you have a 1 here. You have another 1 here when you multiply the two e to the minus and to the e to the plus. And then you have a cos, because you have this guy plus this guy, 2 times cos actually. So basically overall you have 2 times 1 plus cos. So this is a periodic function with period 2w, okay, 2w, which is 0 after w. So w is 1 over 2 tc. So this is why I chose 1 over 2 w. So basically, you can think of so the inverse of the delay spread as the frequency that it takes for the channel response in frequency to change considerably. So if you move by 1 over 2 tc in frequency, then your frequency response changes considerably. So you see that it's really the dual. So before you had the fading is how fast the channel changes over time, and 1 over the delay spread is how fast the channel changes over frequency. So it's really dual. So this is really to sum up. So we have 4 main actors. And by the way, all this Doppler spread, coherence band, delay spread, coherence time, we've already seen it in the toy example of two waves impinging on the receiver. But there it was really a bit stretched because we were talking about still about ideal cosine and something over the air at a very high frequency. While here we are really talking about this baseband model that is what is actually happening in the transmitter and the receiver. So you can think intuitively, you can understand intuitively from the toy examples, but then it's really nice to find the same terminology in this much more close to the reality still example, because it's still an example. It's still a toy model. But why is it a toy model already? Because you cannot transmit sync, for example. Sync means that you already know what you will transmit in 1 year. because sync is symmetric in minus t and plus t, and so basically what is actually done is to send. I think there are the people that know much better than me, but some let's say smooth cosine function that really basically fade out fairly smoothly. Anyway, so just to tell you that this is still a time model, but we can already do something about it. So the 4 main actors is 2 in time and 2 in frequency, and they're always related to each other as 1 over the other. So we've seen the coherence time during which the channel can be considered as constant. 1 over coherence time is the delay spread. So basically, this tells you how fast the channel changes in time, and you want to see, and this is basically feeding. If you want to know how fast the channel changes in frequency, you basically have these 2 concepts here: delay spread, and 1 over the delay spread is exactly the coherence spread. So this coherence really tells you a lot about your channel, how fast it changes over time and over frequency. And why is it important, this coherence bandwidth? Because basically what you do usually is to transmit different things over different frequencies. So you have the interest of knowing whether you're transmitting over basically different channels or the same channel. And then I also wanted to give let's say a cheat sheet of terminology. So we're talking about always fading, but often you hear about fast fading, slow fading, flat fading. Actually, I think that there is no really clear and established terminology for all this thing, but let's say that fast fading can be seen as a channel where your coherence time is smaller than the delay requirements. So basically what it means, so you have something to say, you code it over symbols, and these symbols can be actually sent over different realizations of H, because indeed the coherence time is smaller than the delay requirement. So basically it means that you're saying the same thing over time over which the channel is changing. So this is why the fading is fast. Fast is not an absolute terminology. It's fast with respect to what you want to do. If you want to send something that I mean is about the same thing over 10 minutes, you should basically take into account that the channel for sure will change. So the fading in this case is fast, because it's fast with respect to this 10 minutes. Slow fading the inverse. So basically you code you want to send something, and and basically each symbol experiences the same realization, which may be good or bad. I mean, I'm not telling you that this is so fast fading looks bad, but it can be actually seen as an asset if you do some the diversity coding. But I'm not talking about this now. Flat fading basically it's rather in a frequency. So it means that the W is the frequency at which of your signal, which is much smaller than the frequency of coherence frequency, the coherence bandwidth. So coherence bandwidth is the frequency span over which the channel does not change. So basically, your signal sees a flat thing, because the frequency scale at which the H varies is much larger than W. Frequency selective fading is exactly the opposite. So you're transmitting something, and your channel response is very volatile inside with this frequency. So you see, we already have 4 different terminologies of fading, but they do not say the same thing. And also, last thing, the underspread channel. So basically, when H can be considered as constant over time, when the time of coherence is much smaller than the delay spread. But okay, this is slightly less important. But what is really important is this 4 terminology. Basically, they look like the same thing, but they're very, very different concepts. Yeah, I'm done. Yeah, I also wanted, but it was so ambitious to tell you how one can get rid of the intersymbol interference. So here you have, in general, you have something like that, which is not really nice because each symbol. So what you see here at time L is actually a superposition of different symbols. What you usually want to do is just have one symbol at a time. And there are ways like OFDM. You may have heard of OFDM. OFDM is really one of the ways, but basically the main way in 5G and 4G to get rid of this and to have each ym equal to h of 0 times x of m. And from there, things get really much neater. So, but yeah, I will not tell you about this. So yeah, I'm done. Sorry, it was maybe too long. But...
Questions? I had a little one. I think I know the answer, but just to confirm.
So don't ask.
Your last slide, please. Yes. So here, so there are 2 and 2 options, excluding the last one. So every 4 members of the Cartesian products are possible, like fast fading and frequency selective fast fading, slow flat fading, fast flat fading, and so on. technically.
Technically speaking, I think so. Yeah. I'm not sure how to assign the probabilities between all these pairs, but yes, technically speaking, yes, it's really different things. Yes.
In fact, I was wondering the same. I was wondering if there were a relation between TD and TC, but apparently you can have everything. So,
yes. So, and also I don't know much more than what I told you.
The
But
last line that told me you can have.
Yes, you can have all combinations. All combinations. Then I indeed I don't know what is the more
Not very familiar.
reasonable, but yeah.
But a small terminology comment. There is a beautiful, which really elaborates on what you presented. There is a beautiful statistical theory of fading. If rather than one path, you consider a large collection of reflection paths, then one can leverage the central limit theorem or a version of it to devise classes of statistical fades. For instance, the Rayleigh fade is really based on the central limit theorem, and it amounts to multiplying the power of the signal by an exponential random variable. And it's linked to the Rayleigh distribution when you look at the power.
Right.
And this is there is a rich terminology of fades. There is the Rice fades, which has the direct path plus this central limit scale, Nakagami, and so forth. So there is a big, and it is centrally based on what was presented, plus a sort of aggregation where you don't want to look at what happens for this configuration of this reflector and this, but you average out over a large number of reflectors, and then you get the statistical properties of what the power attenuation or amplifications looks like. And it's a beautiful theory. There is a probabilistic complement to it. But if you plug this the statistical level on top of these equations, you find the basic ingredients of these names that you must have heard of Rayleigh, fade, Nakagami, Rice, and so forth. So it's but it only leverages fundamentally what was presented plus the central limit theorem or certain versions of it.
Yeah, absolutely. And indeed, if you want, all these slides are really taken from the fundamentals of wireless communication by David Shea. And in the same chapter that basically I covered, the last section about Rayleigh and duration fading, I think. So
yes.
I meant to go over it, but it was maybe too much. But yeah. I mean, I cannot say that I'm an expert, but I know what you said about yes.
Yeah, the treatment of say of Rayleigh fade is very beautiful, and so that's illuminating, and this use of the Lindeberg version of the central limit theorem. So that's extremely nice. So, but essentially, indeed, it is the same machinery, right?
Yes, indeed, and indeed, when I thought about making this seminar, I said to myself that there are many mathematicians at Links that there maybe do not work on wireless because there is really this barrier of entry of terminology. But once you know terminology, there's really beautiful stuff behind. So I hope.
Yes, and for instance, the theory of MIMO is fundamentally based on the identification of channels between multiple emitting, transmitting antenna elements and receiving antenna elements, and based indeed on the coherence distance. Some people assume that you have independent Rayleigh fades over this for this gain matrix now, and so the statistical part is very essential in assessment of ergodic properties of channels, and so it was of course not known at the time of the Vishwanath Che book, but I mean the modern things with where when you do massive MIMO, you would see, I mean, these matrices with of independent relay fates and then spectral properties of these, and so one needs to indeed, as you say, to have the understanding of first the physics as you presented, plus the statistical things, plus then the statistical properties of the MIMO matrices, the gain matrices that show up in MIMO. Right? So and so beamforming and all these type of things elaborate on all that. It's beautiful. I mean, it's a fantastically beautiful theory.
I agree, and indeed, if you have some basic references that you want to share with us, I mean,
what we could do is go through the. I mean, but partly, I mean, remember Guodong gave some elements of this famous paper by Emre Telatar, which establishes the link of the gives the capacity, the channel capacity of the MIMO channel, right? And so it goes through a link a gain matrix, which is exactly what was you introduced, but pairwise for every element of antenna in transmission and every element of antenna in reception. And for instance, when this gain matrix is made of IID relay fades, then I mean, I mean, by analyzing the spectrum of this random matrix, I mean, what the capacity is, basically the Shannon capacity. So it's absolutely amazing. And this is one fantastic paper is the Emre Telatar paper. I think it's cited 15,000 times. The Emre Telatar was at Bell Labs, actually. He's one of your colleagues, and he's now with EPFL, right? So with this MIMO capacity, Shannon capacity formula for the MIMO. So that would be one of the central papers, right? Elaborate exactly on that.
And he's the same one who invented the polar codes, right?
I beg your pardon?
Polar codes were also invented by Telatar, I guess.
Yeah, he's a famous information theorist, very, very strong. Yeah, so we should invite him at Links.
Yes.